Good afternoon, everyone. So let's start the session. And it's my great pleasure to introduce Rita Jimenez from the Universidad Nacional Autónoma de México. And today she will talk about unspecified spaces of mapping class groups. So Rita, you can start.
Thank you, Jorge, for the introduction, and thank you to the organizers for the invitation and the opportunity to speak about my work. So let's see if I can make this work. So today I'm going to talk about classifying spaces, in particular for some families of subgroups in the mapping class group. So here's the plan for the talk. So let me recall first the usual definition of classifying a space. I'm going to be trying, I don't think I can make this work. So, I'm going to be considering G a discrete group, and I want X, a CW complex, to be a model for a classifying space BG. If X is connected and it has universal cover, contractible, and secondly, I want the fundamental group of the CW complex to be isomorphic to my group of interest. And you may have seen these examples of these classifying spaces. For instance, you can think of the circle, its fundamental group is Z, and it has a universal cover real line, which is contractible. So this is a model from Z. But there are other models that you can come up with. For instance, if you take S1 cross any contractible CW complex, it's going to give you another model. And so another example is given by the n-fold product of circles, which give you a model for the classifying space of a free abelian group of rank N. And if you have a group like the free group F2 on two generators, you can take the figure 8, that is to say the wedge product of S1 with S1, and it has fundamental group, the free group on two generators, and its universal cover is a 3, so it's contractible. So it's one example of a model for that case. And it's good to have in mind a non-example. RP2, for instance, it has fundamental group Z2, but it's not a model for that because the universal cover is not contractible. And a model is given actually by RP infinity. And I want to point out in this example in particular, this model is of infinite dimension in opposition and contrast with the other examples. So classifying spaces are related to G bundles. And things that are well understood is that these models always exist in a unique optical homotopy. And the second thing that I want to point out is thinking about the definition in a slightly different way that is going to be useful for the second definition that I'll give later. So X is a model for BG if its universal cover X tilde is contractible, but it also is a CW complex that comes equipped with a cellular action by the group G. And we want this action to be free. So that means that the isotropic groups are going to be trivial. So you can think of the universal cover X tilde as a model for the total space EG. And I'll come back to this definition in a bit. And well, these classifying spaces do classify things. They classify principal G bundles. There's a universal principal G bundle, and the isomorphism classes of principal G bundles over a given space up to isomorphism are in a bijection with continuous maps from Y to BG up to homotopy. And as Miguel was mentioning in his talks, the cohomology ring of these classifying spaces give characteristic classes for these G bundles. And in the context that we are dealing with, G is discrete. So this classifying space BG is an Eilenberg-MacLane space of type KG1. And in particular, the homology and the cohomology of this space gives you the homology and the cohomology of the group. So in general, for computations, it's going to be useful to have nice and small models for BG, and I'm very lousy about what I mean by that. But in particular, a way that these models can be small is in terms of dimension. So we would like to have models that are of the smallest dimension possible. And this leads us to the definition of geometric dimension of the group, which is the minimum integer such that there exists, or BG admits a model of dimension n. And there is an algebraic counterpart to this geometric dimension, which is the cohomological dimension, which can be explained just in algebraic terms of the groups, is the minimum integer so that there exists a projective resolution of Z over ZG of length n. And those invariants are going to be the type of invariants that I'm going to be focusing in this talk. And several things are known about them. So for instance, those two dimensions are zero if and only if the group is trivial. For the free abelian group of rank n, those invariants give you the rank of the free abelian group. If your group has torsion, it turns out that these invariants give you infinity. So it's not an interesting invariant in that case. But a lot of the groups, at least in the area that I work on, have torsion, but are virtually torsion-free. So the meaning of that is that they have a subgroup H of finite index that is torsion-free. And then we can define what is called the virtual cohomological dimension. This invariant also appears in Miguel's talk. And is defined to be the BCD of the group is the cohomological dimension of H, H being the torsion-free subgroup of finite index. A theorem of CERT guarantees that this is well defined. It doesn't matter which one you pick, this number is going to be always the same. And in this context, these two dimensions are related by the following inequalities. The cohomological dimension is always less or equal than the geometric dimension, and they are almost always the same, except the possibility that the cohomological dimension is 2. And it's no, if this implies that the geometric dimension is 2. This is a famous conjecture in the area that was posted in the 50s, and that is still wide open. So we don't know if there's an example where this doesn't happen. And the proof to get the inequality above doesn't hold for this specific case. So with that in mind, I want to introduce a slight variation of the definition, which is the notion of classifying spaces for families of subgroups. So let me start by saying here we need as a starting point a discrete group and also a family of subgroups F. And what I mean by a family is a non-empty collection of subgroups of G that is closed under taking subgroups and closed under conjugation. And the families that I want you to have in mind are the ones that I put in the slide. So on one hand, there is the trivial family, which is the smallest family that you can think of. In the opposite side, there is the family of all subgroups, so this is the biggest one. And then there are intermediate families, in a way that the ones that I want you to keep in mind for today is the family fin of finite subgroups, noting that it satisfies the definition. And then these families that capture sort of abelian subgroups of my groups, which is the virtually cyclic family. So it has all the subgroups of G such that H is virtually cyclic. That means that it has a finite index subgroup that is cyclic. And a slight generalization of that is given by this family that I'm denoting by Fn. So n is fixed, and I want subgroups H of my group G such that H is virtually a free abelian group of rank R, and the rank can go from 0 to n. And notice that with this definition of Fn, the family of finite subgroups is just F0. The family of virtually cyclic subgroups is just F1. And these families are sort of nested, just by the way that it's defined. And well, I'll come back to this, but maybe for the rest of the talk, you can keep in mind the family of finite subgroups as a leading example. And so with these ingredients, I want to define the notion of classifying space for a family. So I need a group and a family of subgroups. And I say that a model for the classifying space for the family F, and I'm going to be putting F in the notation so that I remember that, is going to be a G0W complex X. And I want to ask for all the isotropic groups of the action of G on X belong to the family. So the difference between this notion and the one before is before we have a free action, so all the isotropy is trivial, and here the family is capturing the isotropy of the action. And then this classifying space is going to be sort of a universal object in the sense that for any other G0W complex Y that has the property that the isotropic groups belong to F, there is of the G homotopy a unique G map from that space Y to my classifying space or my model of the classifying space. And That is to say, this is a terminal object now, proper to the category. And in particular, for the trivial family, this sort of classifies free G-CW complexes. And for the family of finite subgroups, this classifies G-CW complexes with finite isotropy. Or in other words, people often call this also the universal space for proper actions. So some properties or something that is useful about these classifying spaces is having a homotopy characterization of them. So as before, these models always exist. And if you have two of such models, they are G homotopy equivalent. So it makes sense to talk about the classifying space. And the next point in my slide is to emphasize that a way to identify a model for a classifying space for a family F is by considering a G-CW complex X that satisfies the following condition. So if I pick H, any subgroup of the family, and any subgroup of the group, if the subgroup belongs to the family, and I look at the set of fixed points by the group, that is what I'm denoting by X upper H. This is going to be contractible whenever H is in my family. And if H is not in my family, this is going to be empty because, as I mentioned before, the isotrope is going to be living in the family of subgroups. So notice that from this definition, we can look at what happens when the family that you consider is a trivial family. So if that's the case, a model X for the classifying space with respect to the trivial family, A trig G, satisfies that the set of fixed points of the only subgroup there, which is the identity, is the whole space X, and it must be contractible. And all the isotropic groups belong to the family, so all the isotropic groups are trivial, and then my group acts freely on X. So notice that with that in mind, the quotient of X by G is going to give you actually a model for BG. And what we are calling here the classifying space for the trivial family is nothing else but the total space. So in that sense, this notion is generalizing the one that I was introducing before. And some examples maybe to have in mind. If you have a point and you consider the point as a G space, this is always going to be a model for the classifying space with respect to the family of all subgroups. And maybe a more interesting example is consider the infinite dihedral group, the infinity, is given by the presentation that I wrote there. And it's also isomorphic to a free product of Z2 with Z2. Notice that a model for ED infinity is given by taking the universal cover of the wedge of RP infinity and RP infinity. And notice that this model is going to be infinite dimension. And that's expected because this group has torsion. So we commented before, these dimensions are going to be infinite in that case. And I want to contrast this with what happens when you consider the model with respect to the family of finite subgroups. In that case, a model is given by the real line. You can give a structure of CW complex by taking the zero simplices to be the integers and I'm sorry, I did something wrong. And the one cells are going to be the intervals that are attached to the integers. And I can give an action of my group by making the generator S act as a reflection through 0 and the generator R as a translation by 1. And with that, this satisfies the definition of being a classifying space with respect to the family of finite subgroups. And I want you to notice that in contrast with what happens with the trivial family, this example has finite dimension, actually has dimension 1, so it's a small dimension. And somehow the isotropic groups are helping making the dimension down as opposed to what happens when the family that you are considering is the trivial family. And again, the same philosophy applies. We want nice and small models for these classifying spaces so that we can use them for computations in principle. So again, I want to focus on being small in terms of dimension. And the natural extension of the definition is the following. We call the geometric dimension of G with respect to the family to be the minimum integer such that there is a model of that dimension. And there is also an algebraic counterpart, which is the cohomological dimension of the group with respect to the family, that is also given in terms of length of projective resolution in an appropriate category. And again, they satisfy the inequality as before, but in this case, the Eilenberg-Ganea, there are examples where the Eilenberg-Ganea conjecture doesn't hold. So there are examples of families and groups that are known to have dimension 2. The people who have been studying this problem, this was one of the attempts to solve the Eilenberg-Ganea conjecture in general, but still not enough to give solutions about the more general problem. Some facts about these dimensions. Well, notice from the definition, the geometric dimension with respect to a family is 0 if and only if the group is in the family. For the trivial family, this just recovers the invariant that I mentioned at the beginning. If my group is torsion-free, then the family of finite subgroups is the same as the trivial one, so the invariants are the same. And I like these two beautiful theorems on the subject that are the first one to Stalin says one. And it says that these invariants really describe or characterize three non-trivial groups. So if you know that these invariants, these dimensions are 1 with respect to the trivial family, that means that the group is free and non-trivial. And Dunwoody had a result of the similar flavor, but for the invariants with respect to the family of finite subgroups. So if your group is finitely generated and you know that these dimensions are equal to 1 with respect to the family of finite subgroups, this is equivalent to the group being virtually free. So I think that those are nice instances where these dimensions completely characterize the sort of structure of the groups that we are considering. And an instance or like a reason why people are interested in such classifying spaces, in particular with respect to the family of finite subgroups and the family of virtually cyclic subgroups, is because they appear in the statements of the isomorphisms conjectures of Baum-Connes and Farrell-Jones. And I'm not going to go into the details of what these conjectures say, but the sort of idea is that K-theory is hard to compute, the topological and the algebraic one. And these conjectures establish a connection of K-theory computations with computations in homology of these classifying spaces. In the case of the Baum-Connes conjectures, with the classifying space with respect to the family of finite subgroups, and in the case of the Farrell-Jones conjecture with respect to the family of virtually cyclic subgroups. And these conjectures, and here is one of the reasons why it's important to have nice models, because homology computations are in principle more attainable. And if you know what is the minimal dimension that one of such spaces can have, you know that the homology is going to be 0 after the dimension. So it's useful to have the knowledge of the dimension, even if you don't have explicit models sometimes. And these conjectures have been proved for a large class of groups, of discrete groups. And one of the classes of groups that they are known to hold is for mapping class groups. And those are relatively new results. In particular, the Farrell-Jones conjecture was proved for mapping class groups a bit earlier than 2019, but it was just published in 2019. So this is sort of one of the motivations of why one would like to study this type of classifying spaces. So this is a good point to sort of switch gears and go to the family of groups that I'm going to be considering today. And well, Miguel already introduced them, so I'm just going to be refreshing that definition. I just recall the classification theorem of surfaces that says that for every compact orientable surface, there exists parameter G and R, G the genus and R the number of boundary components, so that S is always homomorphic to a surface SGR, where SGR is the surface of genus, the standard surface of genus G with R boundary components. So these surfaces are completely determined by these two parameters up to homeomorphism. And the mapping class group is a group that wants to capture symmetries or topological symmetries of these surfaces. So if I fix, for the context of the talk, mainly my surface is going to be compact and orientable. and maybe it has a finite number of punctures, and a natural group that captures the symmetry is the group of homomorphisms of the surface, but it's a group that is too big. So it has a topology, the compact open topology, but this makes it a very big group. So people study a quotient of this group, which is the mapping class group that was already introduced. And as Miguel mentioned, there are several variations of this definition. For the purpose of this talk, I'm considering homomorphisms of the surface that restrict to the identity in the boundary of the surface and are orientation preserving, and that's my notation. And I'm considering this group with the compact open topology and taking the group of connected components. So pi 0 of this, or another way to think about this is a quotient of the homomorphism group by the ones that are isotopic to the identity. And if my surface has punctures, this mapping class group acts on the set of punctures, it permutes them. And this action gives rise to the short attack sequence that I'm putting at the end. And the kernel of that action is a subgroup that is of interest to us as well, which is called the pure mapping class group. And I'm denoting this with P mod to emphasize the difference. And you can think of the mapping classes or the pure mapping classes as the ones that fix point-wise the set of punctures. Included in this so much. So when my surface is closed and has genus G and has some punctures, I'm going to denote it by SGN. And I'm going to use the abbreviation mod sub GN and P mod sub GN when I'm referring to the corresponding mapping class groups. So examples of these groups, Miguel already mentioned some of them, are the mapping class group of the disk or the puncture disk. It's going to be a trivial group. And this is the Alexander lemma. And this can be used to prove that the mapping class group of the sphere, the functional sphere, is also trivial. And it's good that not all of the examples are trivial. So for instance, the mapping class group of the annulus is known to be an infinite cyclic group generated by the then twist of the annulus. And this example was mentioned by Miguel as well. The mapping class group of the torus or the puncture torus, both of them are isomorphic to the group SL2Z, so the group of matrices 2 by 2 with integral coefficients and determinant 1. And it is also other classical groups that appear in this incarnation, which are the classical Artin-Braid group and the pure Braid group, which is a subgroup. So those examples, you can keep them in mind to recall what is the difference between the non-pure version and the pure version of the group. So those are the mapping class groups of the disk with n punctures. And well, several properties. This group has been intensively studied, and several properties are known. Those groups have the advantage of being discrete groups, so they can be considered in the setting that I was introducing at the beginning. They are finitely generated and finitely presented groups, and in general, they have non-trivial torsion. And so in general, the CD and GD is infinite. So the models of the classifying spaces for the trivial actions are infinite dimensional. But those groups are also virtually torsion free. So we can consider the BCD of these groups, for instance. And here, I just wanted to sort of emphasize, Miguel already talked about this nice analogy between studying mapping class groups and studying vector spaces. And how the analogy of studying the general linear group and the mapping class groups as groups that capture symmetries of these fundamental objects and can be used to classify on one hand vector bundles and on the other hand surface bundles, and how the cohomology of the classifying space of the general linear group gives you characteristic classes for vector bundles, and the mapping class group is going to give you characteristic classes for surface bundles. This is something that Miguel already mentioned in his talk. And in one case, we know completely the answer. In the other one, the cohomology ring is far from being understood. So there is lots of progress on that direction, but there are lots of questions as well. And that is one of the motivations of studying this group. So let me see how am I doing on time. Yeah, so maybe I'm going too fast and I apologize. So I want to use these ideas to go back to the purpose of my talk, which is to give you an overview of what is known of classifying spaces for families of subgroups of these mapping class groups. So let's start with an example. The mapping class group of the torus with one puncture is the group of matrices SL to Z. So it's a familiar group that people understand very well. This is isomorphic to an amalgamated product of finite cyclic groups. And then notice it has torsion, so the geometric dimension is infinity. So that's easy to see just from the group itself. If you consider the family of finite subgroups, then there are models for the classifying space with respect to that family. One of these models is the hyperbolic disk that you can think in terms of Teichmüller space if you want. This has dimension 2. And another model for this classifying space is the Ferri graph. And this has dimension 1. And actually, this geometric dimension in this case is known to be 1 because the group is actually virtually free. And this theorem of, and it's finally generator. And this theorem of Dunwoody told you that virtually free groups are characterized by this invariant. If you go back to other families of subgroups, for instance, we talked about the family of virtually cyclic groups. This geometric dimension equals to 2, and this is a consequence of a more general theorem that says that any hyperbolic group has this condition. That is due to a colleague from Mexico, Daniel Pampinera and Ian Murray from a while ago. And so in particular, we know that this dimension is 2 as well. And then if we consider the other families that I was talking about, the Fn families, it turns out that these dimensions, the corresponding dimensions, are also 2. And this is just because this group doesn't have a billion subgroups of rank bigger than 1. So these dimensions stabilize there. So this is the complete answer for this case. And one would like to have an answer of this sort for general mapping class groups. So a model for the family of finite subgroups of both the mapping class group and the pure mapping class group is given by Teichmüller space when the surface is of negative Euler characteristic. And this Teichmüller space, I'm not going to go into the formal definition, but it's a space that parameterizes equivalent classes of Mark hyperbolic members. This is a way to think about it on the functional surface. And there are several properties that have been studied about this space, but let me just emphasize the ones that have to do with the notions that I'm highlighting today. So first of all, this space is known to be homeomorphic to a contractible space of dimension 6g minus 6 plus 2n. There is a natural action of the group, of the mapping class group, both the pure and non-pure, on the Teichmüller space. And this action is known to be properly discontinuous. And the consequence that matters for the purpose of today is that all the isotropic groups are finite. So the family of finite subgroups is one to consider in this instance. This space has a structure of a CW complex that is compatible with the action. And remember, we have this homotopy characterization of these spaces. We need to look at sets of fixed points. And for any finite subgroup of the mapping class group, the set of fixed points is known to be non-empty. And Miguel already mentioned this in his talk. This is the Nielsen realization theorem, or this equivalent way to think about it. And also the Nielsen realization theorem can be used to show that this set of fixed points is contractible. So this is sort of all the ingredients in the homotopy characterization. And the conclusion from that is that the Teichmüller space is a model for the classifying space with respect to the family of finite subgroups of both the pure and non-pure mapping class group. And it has dimension 6g minus 6 plus 2n. This Teichmüller space gives us yet another beautiful connection of mapping class group with a space that is important in algebraic geometry, which is the moduli space for Riemann surfaces of genus G and N-mark points. Turns out that the quotient of Teichmüller space by the action of the pure mapping class group is this moduli space. And since this action is properly discontinuous, whenever your group is torsion-free, all the isotropy is going to be trivial then. And this classifying space is going to give you a model for the classifying space. This Teichmüller space is going to give you a model for the classifying space with respect to the trivial family of the pure mapping class group. And that means that you can compute cohomology and homology of the group. It's the same as computing homology or cohomology of the moduli space, even with Z coefficients. In general, these mapping class groups have torsion. So Teichmüller is not such a model, but still, the fact that the isotropy groups are finite allows to give a beautiful relation between the rational cohomology. And I mentioned before, this is another reason why people study cohomology of these groups. One is the classification of surface bundles, and this is another one. And I mentioned before, this is far from understood. I like to present this picture. This is in a book in an article by Dan Margalit. He compiled a series of problem questions and conjectures about mapping class group in 2019. And here's an illustration of what people knew at the time about the cohomology of these mapping class groups with rational coefficients. So in the vertical line, I have the genus of the surface. In the horizontal line, I have the degree of the cohomology groups that are known. This is just rationally, and this is just for closed surfaces. And all what is in white is known to be trivial. All what is in black are computations that are known. And so the lines that I have here are the stable homology and cohomology, these famous results by Harrer, the stability theorem, and by Madsen and Weiss, who computed what is it. And Miguel also referred to that in his talk. And then I put in different colors the other bunch of results that I'm not going to be talking about today. But what I want to highlight with this is that each of these colors represents a completely different technique. And what is in gray in the picture is what is not known. And this is just at the level of groups. The ring structure is far from being understood. So this is this is an aside of what I'm telling you in this talk, but I wanted to highlight how complicated this is, and this is also a problem that I'm interested in, and I have a bit of contributions in that direction as well. But let's go back to classifying spaces for mapping class groups, and let's focus in the case that we have pure mapping class groups. I mentioned before, these groups are virtually torsion-free. And one can ask about the BCD of these groups, and this has been computed in the 80s by John Harrer. And in general, when you have a group that is virtually torsion-free, the BCD is a lower bound for the geometric dimension with respect to the family of finite groups. Actually, Brown asked in general, which groups satisfy that these invariants coincide? And there are examples where that is not the case. And then a natural question in our context is, well, we do have a model, which is Teichmüller space, but Teichmüller space has dimension way bigger than the BCD. So a natural question is, are there models of smaller dimension? And this is a bit as what happens with SN2Z, that we have hyperbolic plane of dimension 2, but also the Farrell graph of dimension 1. So we can have several models, but some of them are of better dimension than others. And turns out that when your surface has at least one puncture, Harrer defined in the 80s a spine for Teichmüller space. And so what he considered is an ideal triangulation that Teichmüller has. And this was done by the work of Thorsten Lomford and several others. Can be given or described in terms of arcs and the surfaces. And by an ideal triangulation, what I mean is that I'm putting this as A minus A infinity, because I'm thinking of A as a simplicial complex structure, and then I'm removing some of the simplices. And I think the picture there is the one that really explains the definition, as that is Teichmüller space for genus 1 and one puncture, which is a hyperbolic disk. And I'm putting a bit of the Farrell complex. I'm not putting everything because I cannot, but this is like a part of the Farrell complex. And notice that it's a triangulation, but all the vertices of my triangulation are on the boundary of the hyperbolic disk. So I need to remove them from the triangulation, so that's what I call an ideal triangulation. And these ideal triangulations exist in general. And what Harrer did was to use this ideal triangulation to construct an equivariant refraction with respect to the action of the pure complex group onto what he called a spine, or is called a spine. And he computed the dimension of this spine. So this spine in general is going to give you a model for the classifying space of my group with respect to the family of finite subgroups. And when you just have one puncture, the dimension is going to be minimal, it's going to be divisible. So answering my question for this case, Harrer is giving the answer that this spine of Harrer is giving the answer that the geometric dimension with respect to the family of finite subgroups is precisely the divisible of the group when you have exactly one puncture. And then we were studying this paper of Harrer to do something else, and we realized, I mean, the spines are well defined, but we noticed that there was a mistake in the computation of the dimension when n is greater or equal than 2. So it's actually almost the minimum, but it's not. We need to add a 1 in that case. So the spine is a model, but it's not of minimal dimension. And this is joint work with Nestor Colin, Porfirio, León, Álvarez, Jorge, Sánchez, Saldaña, some collaborators from Mexico. And I mean, it was sort of a bit disappointing that this explicit model is not of minimal dimension, but still you can use Harrer result to compute the geometric dimension in this case by a more algebraic method. There is this beautiful Birman-Sachs sequence that allow you to relate groups with the different match points. And using that and results of Dunwoody and Luck, you can really, like, in an algebraic way, show that the geometric dimension in this case is also divisible. So this implies that there is a model, it's just not the spine. The spine is not of minimal dimension. And the reason why we were revising the work of Harrer is because we wanted to look for a spine for technical space of non-orientable surfaces. And here I'm taking advantage of Miguel's presentation because he talked about this in a more proper way. So I'm just recalling that if I start with a surface of genus G with 2 n-mark points, and I consider orientation reversing evolution, this allows me to define the double cover, the orientable double cover. And as he explained to us this morning, there is a monomorphism between the pure mapping class groups of the non-orientable and the orientable cover. And there is an embedding of the corresponding technical spaces where the image of the embedding is identified with the fixed points by the action of sigma in the technical space of the orientable double cover. And it's not hard to show that this is actually a model for the classifying space with respect to the family of finite subgroups of the pure mapping class group of the non-orientable surface. And what we did, and I mean, we haven't finished it, but we hope that in a month or so it's going to be out in the archive. We use her spine to construct a spine for the technical space in this context. And this spine doesn't have the right dimension just when n equals 1 as before. And so in particular, that means that this geometric dimension in this case equals the BCD when you have exactly one equal than before. This is sort of a consequence of all this and Harrer's construction. So something that I need to emphasize is that for all these constructions of the triangulation and the spines, it's needed at least to have one mark point in the surface. But we would like to know the answer of this question also for closed surfaces. So what can we do when we don't have mark points? So Harrer construction is not going to work there because we don't need the mark point in the surface to be able to do that triangulation and that spine. And in this case, and it's a question, and I think people care about knowing if technical space for a closed surface accepts a spine of the minimal dimension or not. And I believe Thurston proposed one that later was disproved that it was really a spine of minimal dimension, and there is a debate of whether this exists or not. But what I mean to say is that the construction that Harrer did is not applicable in this setting. And in terms of answering the question there, Javier Amayona and Conchita Martinez Perez from Spain answered the question by using algebraic methods. So they computed the geometric dimension for finite subgroups of the mapping class group of a closed surface. So they didn't give an explicit model, but they computed this algebraic invariant, and by computing the cohomological dimension, they got the geometric dimension, and they proved that it equals the BCD. And this implies the existence of a minimal model. But their techniques is sort of an indirect way to do a more algebraic approach. And it depends on showing this first instance, when you have a virtual torsion-free group, G, if you can show that any finite subgroup satisfies the inequality that I put in there. So the BCD of the Bail group of H plus the length of H, which is an algebraic invariant of the group, is bounded above by the BCD of the group G, then this implies that the cohomological dimension equals the BCD. And so by using this more sort of algebraic characterization, what they did was consider subgroups of the mapping class group, finite subgroups, and computing that this bound is established. And they could do it for genus greater or equal than 3. Actually, the surface has genus 2, this doesn't hold. So you need to look for another way. And so using this strategy, we were able as well to prove similar statement when the surface has genus G and has M punctures, but we're dealing with the full mapping class group, not the pure one. Something that we noticed when we were reviewing this is that in the literature, people misquoted Harar's constructions a lot. And so they claim that this was true, but Harar construction just works for pure mapping class groups. So in order to prove this, we would like to have explicit models, but we couldn't. So we use this indirect method to show that the geometric dimension of these mapping class groups also equal the BCD. And this is also joined with Nestor Colin, Porfirio, León, Álvarez, and Luis Jorge Sánchez Saldaña. And another team of Mexican mathematicians, Christian Hitberg, Luis Jorge Sánchez Saldaña, and Alejandra Trujillo Negrete, did the same sort of approach to consider the mapping class group of a closed non-orientable surface. And they also obtained that this geometric dimension is equal to the BCD, using sort of the same strategies, or showing that the bound above is satisfied in this case. So, so those results are algebra results that imply the existence of minimal dimension, but of course, the open problem is to obtain explicit geometric models of this dimension. And that we don't know how to do. We need a different idea. So just to finish sort of this overview, I was talking about a billion subgroups of the mapping class group. It turns out that Bierman, Lubotsky, and McCarthy in the 80s proved that every abelian subgroup of the mapping class group is finitely generated and has rank that is bounded by this quantity that depends on genus and n. And hence, if you want to ask about these families of subgroups Fn, notice that they stabilize once you get to rank 3G minus 3 plus n. They are going to be the same. So you can ask about this model up to that point. And well, here in the picture, I just illustrate an example of an abelian group in the mapping class group of a closed surface of genus 4. And so we can ask about this geometric dimension with respect to these families Fn. And when the surface is orientable of finite type and has negative Euler characteristic, this geometric dimension was computed for the family of virtually cyclic subgroups. And this is original ideas from Daniel Juan Pineda and Alejandra Trujillo Negrete that were later refined by Brita Lusinkis and Nansen Petrosian to obtain the following bound. So this geometric dimension with respect to the family of virtually cyclic subgroups is bounded above by the BCD plus 1. And they actually show that the equality holds when the surface is closed. And using sort of inspired by this result in the methods in this paper, we sort of did the generalized version of that. So we bounded by above the geometric dimension with respect to this family Fk of virtually abelian subgroups, and we got a similar bound in the sense that is the BCD plus K. And here maybe I do have time just to sort of highlight some of the key ideas here that are involved in both these proof. The strategies is sort of the same. So it's an induction argument on n being on k being this parameter of the family of k, so the rank of the maximum rank of the abelian groups that we're considering. And for k equals 0, remember the family F0 is the family of finite subgroups. So the base of the induction is a combination of this spine constructed by Harrer, the results by Ramayona and Martinez-Perez, and our result about the mapping class group of surfaces of genus G within marked points. And maybe this is the main reason why we tried to get this result, because this is the base of induction of another theorem that we have. And we realized after it was published that we had a gap in our argument, because this wasn't actually known, and people misquoted that in the literature. So we sort of solved the gap in our proof and in the other proof as well. And so this is the base of the induction. And then the induction step consists in assuming that the result is true for the family Fk minus 1, and using a construction of Luke and Bayerman that gives you a model for the next family, the family Fk. And remember, Fk contains the family Fk minus 1. And I mean, the construction is given in this diagram, and I'm not going to go into the details of what this diagram has, but we want to bound the dimension of the x in the corner. And in order to bound that dimension, we need to bound the dimensions in the vertices. So one of them is given by the induction hypothesis, and then we need to understand a bit better the other vertices on the diagram and be able to bound the dimension. And that we do it first by showing that this ng bracket h, which is called the commensurator, is actually a normalizer in the group. That's one of the first steps. And then we need to do, and I put it loosely, like an algebraic structure theorem about that. We need to know more about this. But once we do that, we can bound the dimension. That's sort of the strategy that they use and we did use. But in order to get this algebraic structure theorem, we need a lot of geometry of the group, actually. And this gives rise to an merely algebraic question, which is the following. So this ng bracket h is what is called the commensurator of h. So it's the element on the group so that h and the conjugate of h are commensurable. So that means that the intersection of these two groups has finite index in each of them. And the normalizer is always included in this commensurator, but the equality may be sharp. The inequality may be sharp. And so what we show is that in the context of orientable surfaces of finite type with a negative Euler characteristic, if you take H to be a virtually abelian subgroup of the mapping class group of rank greater or equal than 1, there is always H prime commensurable to H, so that the commensurator of H is the same as the normalizer of H prime. So commensurators are realized as normalizers, and we have more control of them. And rank 1 is the work of Juan Pineda, Trujillo, Negrete, Musikis, and Petrosian. We generalize this for rank greater or equal than 2. And when I gave this talk in another place, Alan Reed was in the audience, and he asked this question that I put here if someone is interested. And he asked if this is a property that is not satisfied by another type of subgroup of the mapping class group. And we don't know, because the method that we use, we really use the fact that the groups are virtually abelian. We need the specific properties about that. So our methods are not going to be able to answer this question. But it may be the case that for all subgroups, this is true, actually. So I think it's a good place for me to stop. I just wanted to put faces to the people that I named. This is the team of people in Mexico that have contributed to this subject, and that, well, I'm happy to call them friends and collaborators. So thank you for your attention.